Previously, we talked about the reduction mechanism with lithium aluminum hydride in the Aldehydes Ketones 10 video. In this video, we'll go through the mechanism for the reduction of aldehydes and ketones with sodium borohydride. Now, the first step in the previous video, we saw lithium coordinating with the oxygen. Well, sodium isn't as strong as a Lewis acid as lithium. So sodium, we won't show that coordination, and that means that sodium can be in the presence of a protic solvent, so a weak acid. So we will start with a general aldehyde or ketone. We'll add this note that sodium is a weaker Lewis acid than lithium cation. So a protic solvent is used. So this protic solvent, that proton in the protic solvent is what will then have a hydrogen bond, and that will activate that carbonyl. So let's say we have a protic solvent methanol. We talked about how aldehydes and ketones, that carbonyl oxygen, can accept hydrogen bonding interactions from a hydrogen bonding donor molecule. While a protic solvent is a hydrogen bonding donor molecule, we have a hydrogen bonding interaction between the hydrogen in the solvent and the oxygen in the carbonyl. So this H bond, hydrogen bond interaction here activates the carbonyl, carbon double bonded to oxygen. This has a similar effect to the oxygen coordinating to the lithium. Pulls electron density away even further from that carbonyl carbon. So now we have boron with 4 hydrogens. Again, we'll emphasize one bond to hydrogen. It is bonded to 4 and it has a negative charge. This mechanism is concerted. Everything will happen in the same step. Similar to the previous one, a hydride, so the hydrogen with electrons from the bond, are added to the carbonyl carbon. And now that oxygen is already coordinated, or hydrogen has a hydrogen bonding interaction to the hydrogen in the solvent, in this case methanol. Instead of showing that the pi bond goes directly back to oxygen and then the oxygen will be protonated by the protic solvent, this happens quickly where the pi bond electrons will form a covalent bond right away to that hydrogen that's part of the protic solvent, so that very slightly acidic hydrogen. And then in the same step, the bond between hydrogen and oxygen in the solvent, those electrons will create a bond to the boron. So for just focusing on what was originally the aldehyde or ketone, we have the carbonyl carbon still bonded to the 2 R groups. It has a new bond to the hydrogen from the boron with 4 hydrogens. It has a single bond to the oxygen, to the carbonyl oxygen. And now that carbonyl oxygen is now bonded to the hydrogen, the proton from the solvent. So we've already formed the alcohol product in that first step. Then we have boron still bonded to 3 hydrogens, and is now also bonded to the oxygen and the rest of the solvent molecule, the CH3 in this case. So boron still has a negative charge, and we have the sodium as a counter ion. That was also present in the beginning just as a counter ion there. So now, just like in lithium aluminum hydride, that reduction, these hydrides that are still here and bonded to boron are active in further reductions. So again, 1 mole of sodium borohydride can reduce 4 moles of aldehydes and ketones. So now let's write the general scheme here. This is the whole reaction. We've already produced our alcohol desired product. So the general reaction scheme here, we start with an aldehyde or ketone. We add sodium borohydride and a protic solvent. In this case, a protic solvent is required to protonate the carbonyl oxygen. Sodium borohydride provides the hydrogen to the carbon. If there were no protic solvent present, we would end with the alkoxide, so a negatively charged oxygen without a bond to a hydrogen. And then the desired product is the alcohol version of the aldehyde or ketone. Now we've talked about how lithium aluminum hydride is a stronger base, it's more reactive. It can reduce more functional groups or different types of functional groups than sodium borohydride can. So lithium aluminum hydride is more reactive than sodium borohydride. So we'll list a number of functional groups, and then we'll write down if they can be reduced by lithium borohydride or sodium borohydride. All right, we'll start with aldehydes. So we have a hydrogen bonded to a carbonyl carbon, bonded to some other R group. We will include ketones, so 2 R groups, both are carbons. Some additional functional groups we'll consider alkyl halides. So an alkyl group bonded to a halogen, if that's getting reduced, the halogen is being replaced by a hydrogen. Ester is another carbonyl containing functional group where the carbon's bonded to an oxygen and another R group. And then carboxylic acid we've seen before. So sodium borohydride, we know that can reduce aldehydes and ketones. That's what the previous video was about. in this unit. So it can reduce both aldehydes and ketones, but it cannot reduce, it's not a strong enough reducing agent to reduce an alkyl halide, an ester, or a carboxylic acid. Lithium aluminum hydride, on the other hand, can reduce aldehydes and ketones, can reduce an alkyl halide, can reduce an ester, and can reduce a carboxylic acid. So depending on what functional groups you're starting with, it's important to use the reducing agent that will reduce your molecule.